All right, good morning. Hope you guys are having a great day so far, since it's just getting started. If you don't already, I need you to get out your notes from yesterday, the 8.3 notes, the ones that had to do with the Hershey Kisses activity that we did. So go ahead and get your 8.3 notes out, and you need your calculator as well. Get your calculator out. Go ahead and get those two things out. All right, got your notes and a calculator. Okay, cool. So I want to go over these notes. So not the activity, not the Hershey Kiss activity, but I do want to just kind of real quick highlight some things on the notes part, okay? So one thing is conditions, all right? When we are constructing a confidence interval for a population proportion, we need to check some conditions. The two conditions that we discussed yesterday was we need to make sure that we have a random sample. So the sample must come from a random sample. This ensures that our sample proportion is an unbiased estimate. It also means that we can generalize our sample results to the population. Okay, so when we take a random sample, that means that we're able to get an unbiased estimate and that our results will go back and generalize to the population. Then we have our normal or large counts condition. For the normal or large counts condition, this ensures that we can use a normal distribution to model what is our situation, okay? So to do that, we have to just check two things. We have to make sure that our number of successes, which can be found by multiplying the sample size times the sample proportion, and our number of failures, which can be found by multiplying the sample size times the complement of the number of failures. We have to make sure that both of those are greater than 10. This is called the large count condition. All right, now, sometimes you're going to already know the number of successes. Like yesterday, when we were doing the Hershey Kiss activity. For example, you already knew how many of your Hershey Kisses fell onto the bottom. And so your number of successes equaled the sample size times the sample proportion that did do that, but you already knew that that number equaled whatever it was. For example, 24 or however many it was for you, okay? Now, to get the sample, or to do the actual math here, again, what we did yesterday was we took our sample size, let's say it was 50 or whatever. Our proportion of our sample that landed flat would have been the number that landed flat out of the 50 total that we had, which if you see, that just reduces down mathematically to the number of successes that we started with anyway. Okay, so just wanted to make sure and clarify that. Also, our number of failures is the sample size times the complement of the proportion of success. So again, if we had a sample of 50 and 24 of them landed flat, then that would mean that 26 of them did not land flat or failed. And so in that situation, we would have 50 times 26 over 50 that did not land flat. And so we would end up with 26, okay? Now, a lot of times you're going to see that this 1 minus p hat, they kind of just do this in their head, right? So 1 minus the p hat, which is 24 over 50, is equal to 26 over 50. And most people just kind of do that part in their head, so you don't usually see the 1 minus. A lot of students get confused about where did the 1 minus go. So I just wanted to give you guys a heads up on that. Okay? All right, and then Z-star critical values. Z-star critical values, you're going to see in your sapling that it's going to talk about table A. Basically, what I've done is given you guys the 4 most common Z-star critical values from Table A. Table A is just a big, giant table full of data that you look at and find the values or whatever. But this is just the 4 most common ones. A Z-star critical value basically is telling you how many standard deviations you need to go from the middle in order to capture the percent that you want to capture, okay? So from yesterday, we talked about the 68, 95, 99.7 rule. So 68% of our data, right? If I wanted to capture 68% of our data, then I would go about 1 standard deviation or a Z-star critical value of 1 if I wanted 68% of my data. But most of the time we want more than that. We want to capture 90% or 95% or so on and so forth. And so in those situations, our Z-star critical values are bigger. I want to capture more of the data. So for 90%, I need to go from the middle 1.645 standard units or standard deviations. To capture 95%, 1.96. Again, remember, that is about 2. We talked about that yesterday from the 68, 95, 99.7 rule. 98%, we're getting 2.326 standard units. So we're going from the middle 1, 2 standard deviations and even a little more, 0.326. And so that's what these numbers are. It tells us how far from our point estimate, our p hat, we need to go in order to capture a certain percent of the data. And then our final thing that we talked about yesterday was the standard deviation of the sample distribution. This is also called the standard error. Has this formula here. Okay, we take our sample proportion times the complement of the sample proportion, divide by the sample size, and then take the square root of that. And to interpret that in an SRS of size whatever, the sample proportion of whatever you're talking about in the problem will typically vary from the true proportion by about that much. Okay? Putting it all together, again, here we have our general form of our confidence interval. We're going to have our point estimate plus and minus our margin of error. So last week we talked about that as you have your point estimate here in the middle and you add your margin of error. That gives you your high value for your estimate, and you subtract your margin of error, and that gives you your low value for your estimate. Okay, and whatever this low estimate is and whatever this high estimate is become your interval. So you have your low, comma, high, and that becomes your confidence interval. Your point estimate is the direct middle of your interval. That is your p hat, your sample proportion. Okay, p hat is your sample proportion. And your margin of error is made up of 2 things. Okay, the distance that you go from the point estimate out to either side is made up by multiplying these 2 values together. Okay, this is your margin of error. So we have our point estimate, which is our p hat. We have our point estimate plus or minus our margin of error. And the margin of error is made up of these 2 things. The Z-star critical value. Okay, that is what we just talked about a minute ago. Okay, this is our critical value. And that's basically how many standard errors are we going to go from the middle. And we have our, and then we have our standard error, which is this part of the margin of error. and that is our standard error. And that's how many of the standard deviations we're going to multiply. That tells us the value of the standard deviation that we're going to multiply by that critical value. Okay? All right, so let's look at this example real quick, and then you guys can work on your sapling. According to a recent study by the Annenberg Foundation, only 36% of adults in the United States could name all three branches of government. This was based on a survey given to a random sample of 1,416 U.S. adults. Okay? Show that the conditions for calculating the confidence interval are satisfied. So we need to check random. Obviously, we have an SRS of 1,416 U.S. adults, so that one works. And then we're going to check our normal or large count condition. That means we need to check that n times this sample proportion is greater than or equal to 10, and we need to make sure that n times 1 minus the sample proportion is greater than or equal to 10. So n is our sample size, 1,416. It says here the proportion of the sample that could name all three branches of the government was 36%, so that's 0.36. And so we're going to multiply for the sample size of 1,416. We're going to multiply that by 36%. 1,416 times 0.36. That equals 509.76. That is greater than 10. And then we're going to check 1,416 times the complement of the sample proportion. So that would be 1,416 times 0.64. Okay? And when we do 1,416 times 0.64, we get 906.24, and that is greater than or equal to 10. One thing I do want to point out real quick is if you look at what those two numbers add up to, 509.76 plus 906.24, if you add those two things together, you get the sample size of 1,416. That's one way you can check to make sure that your math is right. Okay. All right, let's look at number 2. Number 2 is asking us to calculate the actual confidence interval for this data. So in your notes here, you'll see that it actually tells you some steps. So step 1 says to find the point estimate, okay? So your point estimate is your actual estimate from the sample, and that's going to be our p-hat value. And in here, it says that in a recent study, 36% of the adults in the U.S. could name, and that is based on that random sample. So p-hat would be 0.36. So that's my point estimate. That's going to be the middle of my interval. Now, step 2 says to identify the z-star critical value for 99%. Okay, if you look back on the back side of this example here, you will find the 99% z-star critical value is 2.576. 2.576. Step 3 says to calculate the standard error. The standard error is the square root of p-hat, 1 minus p-hat, divided by the sample size. That is also on your notes on the back side of this problem. So we're going to do the square root of p-hat, which is 0.36, 1 minus 0.36, divided by the sample size of 1,416. Okay, so let's plug that in our calculator. 0.36 times 1 minus 0.36 divided by 1,416 and then the square root of that. And our standard deviation is 0.0128. Okay, and finally, we are going to construct the interval. All right, so construct the interval. I'm going to go ahead and erase this. Let me put this over here. Let's see. We had p hat was 0.36, our z star was 2.576, and our standard error was 0.0128. Okay, just want to make sure I have enough room to do this. All right, so we're going to take, this is step 4. We're going to actually construct the interval now. So we're going to take p hat plus or minus the z star critical value times that standard error that we just calculated, which is this whole big formula right here. P hat is 0.36 plus or minus the z star critical value of 2.576 times the standard error that we already calculated of 0.0128. And now all we need to do is just multiply. We're going to multiply our z star critical value times our standard error. This is going to give us our margin of error. Okay, this is going to give us the margin of error. And we get 0.36 plus or minus a margin of error of 0.03. We'll go ahead and round that to 3, 0.033. I believe it's 0.03297, but we'll just round that to 0.033. So what we're doing is 0.36 is in the middle. We're going to add 0.033 and we're going to subtract 0.033 to get our interval. So the lower boundary of our interval is going to be 0.327. The upper boundary of our interval is going to be 0.393. Okay, again, the middle of our interval is our point estimate of 0.36. I added the margin of error, which was equal to 0.033. That got me the 0.393. I subtracted the margin of error, and I got 0.327. And that's the interval. Okay. All right, and now last step, going to interpret this interval. We're going to interpret this interval. We are 99% confident that the interval from 0.327 to 0.393 captures the true proportion of U.S. adults who could name all 3 branches of government. Okay. So that means basically that we are 99% confident that somewhere between 32.7% to 39.3% of U.S. adults could name all 3 branches of government. So if we took a sample and let's say only 10% of them could, we would think something's going on with our sample. Or if we took a sample and 50% of them could name all 3 branches of government, then maybe we would think, wow, we got a really smart sample. So again, not saying that these are the only answer or the only percentages, but these are the most probable, plausible percentages for the true population. All right, you guys, you have the 8.3 sapling. It is very similar to this. It's a lot of these same kind of questions, okay? So just make sure you're answering the questions based on what it's asking for. Sometimes it only asks you to calculate the standard error. Sometimes it only asks you to find the sample proportion. So just make sure you're answering it based on what it's asking you to do. Okay? I will see you guys tomorrow. Have a great day.